Welcome to the NYU Tandon School of Engineering. Thank you for being here today at the final presentation of the year in our seminar series in modern artificial intelligence. Thank you as well to Tandon Executive Dean Juan de Pablo, who is also serving as NYU First Executive VP for Global Science and Technology, and Senior Vice Dean Ari Odile for their support, and to my own Department of Electrical and Computer Engineering for hosting. I launched this series 7 years ago, and it has been among the greatest honors of my career to see it evolve into a significant event in the AR world and a vehicle for unifying scientific communities around the influential research ideas of today that can have a major impact tomorrow. Those of you who know me or who have been to any of the seminars know that I'm fond of a quote attributed to Albert Einstein. The important thing is not to stop questioning. Curiosity has its own reason for existing. I recently discovered another line I love. It's from the iconic Renaissance writer Zora Neale Hurston, who wrote in her 1942 autobiography, Dust Tracks on a Road, "Research is formalized curiosity. It is poking and praying with a purpose." Isn't that a wonderful description of how many of us here spend our days poking and prying with a purpose? In the case of our guest today, her purpose is to investigate information processing in the brain at the systems level. And her poking and poding involves conceptual, mathematical, and computational frameworks from statistical physics, statistical inference, and nonlinear dynamics. It gives me great pleasure to introduce Sarah Sola and tell you a little bit more about her. Sarah holds a bachelor's degree in mathematics and physics and a master's degree in physics, both from the University of Buenos Aires in Argentina. She earned her doctoral degree in physics at the University of Washington in Seattle. She conducted her postdoctoral poking and praying at Cornell University and subsequently spent several fruitful and exciting years as a member of the legendary neural networks group at AT&T Bell Laboratories in Homedale. She is currently a professor of neuroscience and professor of physics and astronomy at Northwestern University. She will be speaking to us today about statistical physics, neural networks, and neuroscience, and how those intersecting topics evolved from the early 1980s until the present. One of the pioneering figures in that world was John Hopfield, and Sarah has said that after she heard him speak at Cornell about memory storage and retrieval through attractor dynamics, her life was never the same. I predict her presentation today might have a similar transformative effect. So without further ado, please join me in welcoming Sarah Sola to the podium.
Thank you. Thank you very much, Anna, for the invitation and for your very kind introduction. Yeah, I was planning to start with that story. You know, my background is in physics, theoretical physics, and I did my PhD in phase transitions and renormalization group and critical phenomena. And then I went to Cornell University to do my postdoc. I was in with the solid state physics group. And I was working on metal insulator transitions and percolation theory, very honest kind of solid state physics. And I went to a meeting of the American Physical Society, which is a rather large meeting with many parallel sessions. So you study the schedule in advance and you said, I'm going to go to this talk and then this talk and then this talk, and you go around. And suddenly I had a gap in my schedule and I thought, okay, I should go to a plenary talk, not the short talks, because the plenary talks, people try to be a little bit more pedagogical and you can learn something even if it's not your topic. So I walk into this room and there is John Hopfield, whom I had never met. And he was talking about a model, which was essentially a model of spin glasses. I'll tell you a little bit about that today. And I was totally familiar with this model. I understood the mathematics. I understood the landscape with many minima. I understood every equation that he wrote, but he was using this model to talk about storing memories and retrieving memories. And he was talking about putting words and concepts around this mathematics that I never imagined would be connected. And my life really was never the same. I went back to Cornell and we had a tradition because this meeting has so many parallel sessions, we had a group meeting the first 2 weeks. Everybody would go to the board and said, what did I hear at the March meeting that was exciting? So when it was my turn, I go and I take my notes and I explain what Hopfield had done in his talk. And I was a postdoc with Neil Ashcroft. I don't know if any of you know any solid-state physics, but he's the famous author of an Ashcroft and Mermin book that everybody uses to learn solid-state physics. And he's very, very traditional. He was very traditional solid-state physicist. So I finished my talk and he looks at me and he says to me, well, Sarah, that looks very interesting, but it isn't really physics, is it? And I thought to myself, I was not brave enough at that age. I was just a starting postdoc to answer, but in my mind, I answered, I don't care if it's physics or not. That's what I want to do. And that's what I ended up doing. So I'll talk to you a little bit about that path. So we start with real neurons, which are beautiful, absolutely beautiful. And these neurons are, oops, something is not showing at the bottom. Okay. These neurons were first drawn by Ramon y Cajal at the beginning of the 20th century. And his drawings were based in a stain developed by Golgi. This was a silver stain that made a few neurons look very black in the culture. So he would look at them through the microscope and he would make these beautiful drawings. And you can see how beautiful these drawings are. And then Golgi and Cajal took a Nobel Prize in 1906 for this development. This was a Nobel Prize in physiology or medicine. And this is essentially how the neurons work. So the neurons have a body, it's called the soma, this very ramified dendritic tree. And the membrane potential of the neuron changes as it receives inputs. The inputs tend to either depolarize or hyperpolarize the inside of the neuron relative to the external medium. If you think of the extracellular fluid at 0 as ground, the internal voltage is typically -65, -70 millivolts. And then it fluctuates up and down as stimuli comes in, and then when the neuron depolarizes sufficiently, it emits an action potential, a spike. This spike travels down the axon and is communicated postsynaptically to other neurons. So you can think of this neuron as an input-output device. It receives inputs, X1, Xn, for all the presynaptic neurons. These inputs are processed through these dendritic, highly complex and arborized dendritic tree. And then when an action potential is emitted, that effect is communicated as an output to a fairly large amount of postsynaptic neurons. Typically, if you look at a neuron in cortex, that neuron is receiving inputs from the order of 1,000 to 10,000 neurons. So that's a lot of inputs. However, it's a very small fraction of the total number of neurons in the cortex. So for instance, if I think of extending my arm like this, my primary motor cortex, which is just under the handle of your earplugs, fires of the order of 10 to the 6 neurons. You have all the order of 1 million neurons that are related to this movement. So 10 to the 4 is not a very large connectivity compared to the actual size of the population of neurons that participate in any task. So from this beauty, we will go now to a model. And the model is going to be very, very simple. It's going to be a point neuron. This point neuron is receiving inputs. The inputs xi become rates, finding rates that I call R sub I. Each R sub I is multiplied by a strength of coupling wi. You sum over all the presynaptic neurons that give input to this given neuron. So that's the summation part, the linear combination. This neuron might be receiving an input from the outside world, if it's a retinal neuron, or from other areas of the brain. And then this total sum, which is the sum wi ri plus I, determines the membrane potential. This is passed through a nonlinearity, in this case, just a threshold nonlinearity that says, if the membrane potential exceeds the threshold, the neuron will fire. If the membrane potential is below the threshold, the neuron will not fire. So it's just a summation of synaptic inputs, a linear combination with these strengths. The coefficients of the linear combinations are the strengths of the couplings plus a threshold nonlinearity. So when this model came up first, was proposed by McCulloch and Pitts. And I always like to show this because I love the title of this paper. We don't write papers that have these very interesting titles. Oh, you cannot see it. Okay, I'll read it. A logical calculus of ideas immanent in nervous activity in 1943. So okay, I'll read the bottom when it's cut off. So these McCulloch-Pitts neurons then are simply sum and threshold neurons. So you do the sum, which is typically called H in the physics literature, this linear combination of the presynaptic rates with the coefficients Wi. You add a W0, and you can think of this W0 as the I minus the threshold. So there is a bias provided by the external current and a threshold. If you subtract them, that's just a constant that you can add to the linear combination as a W0. And then the threshold is for H equals 0, because you have incorporated the actual threshold in the W0. So if H is positive, the neuron fires. If H is negative, the neuron does not fire. So these guys got very excited because they thought zeros and ones, that's the way a computer works. The brain is like a computer. And this generated a whole excitement and activity that went under the name of cybernetics. And what they thought was really that the brain was like a computer. They said, if this is a neuron, I put neurons together, it's a computer. And they started asking questions about, okay, what kind of things could you do with this kind of very simple neuron? So again, the neuron is just a linear combination of the inputs. You pass it through this threshold nonlinearity. And then what you're doing is you're mapping n-dimensional inputs in which either the input is either a 0 or a 1, because either every presynaptic neuron is either firing or not firing. And then the output is also a 0 or a 1, because that neuron is either firing or not firing. So you can think of this as an input-output map, where the inputs are n-dimensional strings of zeros and ones, and the output is also a 0 or a 1. And the actual transformation, the actual input-output transformation depends, of course, on the parameters, W0, which is this net bias, and then W1, W2, Wn, which we call synaptic couplings, because they are the way in which the presynaptic neurons are connecting to that particular neuron. And so they began to ask themselves, okay, what can I do? Can I do all Boolean functions with this type of simple neuron? So they started, playing games. And I give you here a little exercise to do. If you set all the W's equal to 1, all the couplings equal to 1, and you play with W0, you can implement the AND function and the OR function very, very easily. So they said, okay, maybe this is a universal computer for Boolean functions. Can I implement all possible Boolean functions with this? And the answer is no. You want it close? Is that better? So how many Boolean functions are there? Oh yeah, it is, now I can hear it. From n inputs to one output. So if I have n inputs, if I want to organize this as a truth table, I have a string of length n, zeros and ones. In every place I can put a 0 or a 1. I have 2 to the n possible inputs, right? So I construct my truth table, I have 2 to the n lines on it. And then in either output, I can put either a 0 or a 1 to say what is the truth table. And then I have 2 to the 2 to the n. So there are 2 to the 2 to the n possible Boolean functions. And the question that they ask is, can this McCulloch-Pitts neuron implement all possible Boolean functions from n inputs to one output? And the answer is no. Actually, you will see in a little while that it's a pitiful small fraction of functions that you can implement with this. It is a problem called the linear separability problem. The second problem is, even for those functions that can be implemented, do you need to be like McCulloch and Pitts and sit there and scratch your brains and figure out how to give values to these W's in order to implement that desired Boolean function? Do you have to engineer the problem? And the question is not, you don't want to engineer them, you want to learn the W's. And that poses a very interesting problem, which is the learning problem. And if you look at all the work that I'll tell you about that was done in the 80s, most of this work is addressing these questions, how to go beyond linear separability and how to learn. That's really the spirit of the thing. So before we move into that, because that is more related to the things that we do today with deep learning, I want to talk about John Hopfield a little bit. So John Hopfield had great advantage, which is he was a physicist. He is a physicist. But at that time, he already was a very, very good solid-state physicist. And he said, these neural networks like these, where the rate can be either 0 or 1, and the couplings are the WIs and the W0, look a lot like a system that we all know very well as physicists, which is called the Ising model. So the Ising model is a model of magnetism, very simple, where these little magnets in each atom can either point up or down. So the variable that we call SI can be either +1 or -1. But it's again a binary variable. It's not a big difference between 0, 1 and -1 + 1. It's a simple linear transformation. So in the Ising case, we have couplings Jij and local fields mu I. And in a network of neurons, we would have couplings Wij and Wi0. But he knew something. He knew that the Ising model had an energy function. And the energy function for the Ising model has a bilinear term where spin Si and Sj interact via the Jij, so that's a quadratic term in the energy, and then a linear term where every spin Si experiences a field mu I. So this model, again, you cannot see my bottom line, this model was proposed by a German professor called Lenz in 1920. He gave it to his student called Ising, who completed his thesis in 1925. So what Ising did was put all the spins on a chain and solve what we call the one-dimensional Ising model. And then he thought this was terribly boring. This could never be a model of any interesting magnetic material. And he left physics. And it was a big mistake because we're still talking about the Ising model today, like 100 years later. So, but I don't know what kind of career he had, but not in physics. It turns out that it's not such an easy model to solve. If instead of arranging these spins on a one-dimensional lattice on a line, you put them on a two-dimensional lattice, you get a two-dimensional Ising model. And it took until 1944 to solve it. It was solved by Onsager. And Onsager also got the Nobel Prize in 1968 in chemistry, but for a different reason, not for solving the two-dimensional Ising models. But there are a lot of Nobel Prizes in this field. So if you have an energy function, you can ask what are the ground states of the system. And this is, going back to Anna's specialty in optimization, how do I find the minima of this energy function? Those are the states that are the ground states of the system. So there are different possibilities. Imagine that look again at the energy that I wrote again for you here. We want to minimize this energy. If all the J's are positive, then I want the S's to be the same. If they are joined by a positive J, they are either both up or both down, because in both cases, the product is +1. And then I gain that positive J with the minus sign, I decrease the energy. So in a ferromagnet, when all the J's are positive, all the spins are pointing up or all the spins are pointing down. And those are only the two ground states, which would be equivalent like all the neurons are firing or all the neurons are totally quiet. Not very interesting for the ferromagnet, might be interesting, but not for the neural system. Then you can think of an antiferromagnet where the J's are negative. So now if the J is negative, I want the product Si, Sj to be negative. And how do I do that? One is up and one is down, or the other. One is up and one is down. In both cases, the product is -1. -1 with the minus sign of the Jij again becomes positive. And because the energy has an overall minus sign, again, the energy goes down. So in an antiferromagnet, for instance, if you put it on a square lattice, you again have two ground states, because you put the first spin up, these two go down, and this one goes up. But you could have started with this one down, and then these two go up, and this one goes down. So you have, again, two ground states. But the antiferromagnet is already interesting, because imagine I have a triangle. So I put this spin up, I put this spin down, and what do I do with this one? If I put it up, it's okay with this, but not with this. And if I put it down, it's okay with this, but not with that. And that introduces the concept of frustration, the concept that you cannot satisfy all the bonds in the problem. And this problem of frustration that appears already in antiferromagnet once you move away from a square lattice, is very, very prevalent in the spin glass. In the spin glass, some of the J's are positive and some of the J's are negative. It's a mixture of ferromagnetic and antiferromagnetic properties. And now you have many, many, many ground states because there is a lot of frustration. There is a lot of little circuits where the spins cannot be optimized given the J's around that loop. And that says you could do this, you could do that. It's not perfect, but this is the best you can do. And there are many ways of doing the best you can do, but not perfect. So you end up with a landscape with many, many, many minima. This problem, again, was fascinating to physicists, the spin glass problem. It began to be studied by, and I'm sorry you cannot see the bottom, but I'll read it, Edwards and Anderson in 75, Sherrington and Kirkpatrick in 78, and then Giorgio Parisi studied this, developed a whole methodology to deal with this problem called the replica method, and he worked on it from 1979 to 1983. And Parisi got a Nobel Prize in 2021, just 3 years ago, for this. In this case, it was a Nobel Prize for developing the techniques that allowed us to solve the spin glass problem. So a lot of this was known, and a lot of this was known to Hopfield, right? So he had this fantastic idea of saying, okay, let me make a neural network like this, a recurrent neural network. Let me take the McCulloch-Pitts neurons and connect them, not on a lattice, but connect them in principle, all connectivity. Every neuron is connected to all the other neurons. And we had the same equations like before. The membrane potential of neuron I is the sum of its presynaptic inputs, Wij, Rj, sum over all the neurons that are presynaptic to I. They might be a bias or a current that is injected directly into neuron I. If this exceeds a threshold that I think Hopfield called UI, then the neuron will fire. And if it does not, the neuron will not fire. And then again, so we have exactly the same equations we were having before, where the Wi0 is this net bias, is the bias minus the threshold. And this is essentially the neurons that were used by Hopfield in his 1982 paper. Is the talk that I heard him give so many years ago. Now, there is another advantage for knowing about the Ising model, which is there was a method for finding the ground states, which was called Glauber dynamics and was based essentially on Monte Carlo algorithms and metropolis ideas. So the question is to check all the time whether you're consistent with your environment or not. So let's say I'm fighting, and I'm going to check all the neurons that are presynaptic to me and see if I should be fighting. If I should, then I don't have to change what I'm doing. And if I'm not fighting and they say I should not be fighting, I don't need to change what I'm doing. But if it exceeds threshold and I wasn't fighting, I should change to fighting. And vice versa, if I was fighting, but the total input does not exceed threshold, I should shut up. And so what had happened with Ri, the changes in Ri can, you are 1 and stay at 1, or you are 0 and stay at 0, so there is no change. Or you are 0 and go to 1, there is a change of +1. Or you are 1 and go to 0, there is a change of -1. This is the only possible ways in which this variable can change. And now what you can see is that this energy, you can see if the threshold is met, then either you'll stay fighting or you'll go from 0 to 1. If the threshold is not met, either you stay quiet or you go from 1 to 0. So the delta Ri is either non-negative or non-positive, depending on these two conditions. And what Hopfield showed in his 1982 paper is that if R changes according to this rule, following these conditions, then the energy changes in a manner that the change is always negative. So the energy always goes down. So you start somewhere in this energy landscape and you go down. He never used the words gradient descent because there is no gradient. These are binary neurons. Remember cybernetics, they were still in the world of cybernetics. The only conditions were that the Wij's are equal to the Wji's, the connections have to be symmetric, and there have to be no self-coupling. The neuron is not talking to itself. It's only receiving presynaptic input from other neurons. Oops, I keep on losing things, I'm sorry. The question is, again, how do we get these W's? How do we get the Wij's and the W0s? And then Hopfield we went back to what we know about the brain. And what we know about the brain comes again from Ramon y Cajal very early in the 20th century, and then from Donald Hebb in the middle of last century, when he proposed a mechanism of correlated learning. It was, you can summarize as saying neurons that fire together, wire together. So if A causes B to fire, eventually the strength of the connection from A to B will increase. So there is a building of synaptic connectivity based on the combination of presynaptic and postsynaptic activity. So that's exactly what Hopfield did. Hopfield completely avoided the learning problem. He said, I'm going to use Hebbian learning. I'm going to assume that I have memories that I want to store. All these memories, all the elements of the memories are +1 and -1 elements. Every memory is an n-dimensional vector, so it's a string of +1s and -1s. And I have m such memories. Mu, the supra-index, is labeling the memories. And what I do is I do the outer product of these vectors. So every memory, outer product with itself, gives me a matrix. I sum over all m memories and I divide by m, and that's the connectivity matrix. It's very easy to go from these 0, 1 variables to this -1, +1 variables. And what Hopfield showed was not only you go downhill, but these particular patterns that are the size, the memories I wanted to store, are minima of this energy function. So when I go downhill, if I am in the right basing of attraction, I will recover the memory. And if I am at the memory and I deviate it a little bit, I will go back to the memory. These memories are attractive because I'm moving downhill in this energy landscape, okay? So the idea of Hebbian connectivity allowed him to store these memories as minima. This is the idea that they are fixed points of the dynamics. And then the collective dynamics is what's doing the computation. Now, just move away for cybernetics for a moment and think neuroscience. All the neuroscientists at that time were very busy studying single cell properties. You know, people who make careers out of studying the pyramidal cell in visual cortex or the spiny neurons in the striatum. Very few people had the concept of looking at collective dynamics, of looking at what happens when you create a network of neurons. Even if every neuron is a simple element, you have complexity that emerges at the network level just because of the large level of interactions. So complexity is an emergent property of the network. And it's a collective dynamics that allows the brain to process this information. So the idea that the computations of the brain come through these collective dynamics, and that this collective dynamics has interesting fixed points that are attractors, that are memories that you have stored, were totally revolutionary ideas, both from the point of view of pure computation. Think of a computer. How do you address a memory in a computer? You have to know the address. It's an addressable memory. But in this scheme, you have to have enough information to be in the right basing of attraction. And then the dynamics will take you to the bottom and you'll recover the memory. So it's what people call at that time a content addressable memory. You have to know enough about the content to be the right basing of attraction as an initial condition. And then the dynamics takes you downhill to the fixed point. So this was totally revolutionary. One thing was missing in this idea, and this actually led to a lot of interesting developments, which was to be able to move beyond the binary case. Let's leave cybernetics behind, and let's allow for a firing rate in a neuron, not just firing an action potential or not on a very short period of a couple of 5 milliseconds, but let's look at it over a longer period and look at what rate the neuron is firing and normalize it as 0, 1, where 1 means the maximum firing rate. And again, play the same game, but now the rate is in the 0, 1 range. So the possible states before were vertices of a hypercube, right? N-dimensional strings of zeros and ones. So they sit in the vertex of a n-dimensional hypercube. But now I'm going to allow for the full hypercube to be a possible state, because I'm going to allow for the rays to be numbers between 0 and 1. So I'm not confined to the vertices. Now I can explore. The dynamics become much more interesting for the system. It has many more states to explore. And then you can write, again, a very similar equation in which the matrix W acts on the vector I, R, you sum I, you subtract the threshold, you apply a nonlinearity, and that's a differential equation that tells you how R changes with time. And the steady state solution is that the output rate is the nonlinear function applied to this linear combination. It's the same mechanism as before, except that I'm allowing now the rates to be between 0 and 1. And I could apply it especially to the case of a linear neuron where I don't have a nonlinearity, I just multiply by a constant. So this is exactly what Hopfield studied in his 84 paper. He studied this system where the variables are now were between 0 and 1. And again, you have n such variables. And again, once more, he showed that if you assign to every state within this n-dimensional hypercube an energy in the same energy as before, the dynamics of the system given by this equation is such that the energy monotonically decreases. So then there are these drawings. For instance, here you see, here the variables are not 0, 1, but minus 1, 1. We go back and forth between these two demonstrations, these two notations. But this is a two-dimensional state space, and this is the energy function, and you can see that there are 4 minima, and that there is a saddle point that separates the basing of attraction of all these minima, so that decides where you go downhill. So this idea of basins of attractions controlled by a fixed point was one of the seminal ideas that we learned from Hopfield. Still, we have a problem, which is if we want to go beyond Hebbian and we want this recurrent network to do something more interesting than just simple association of that type, how do we learn? We still have the learning problem. How do we find interactions Wij so that the population dynamics out of T has fixed points at the desired memories, and we get the correct basins of attractions to be able to perform associations? This again attracted the attention of physicists, and there are 2 beautiful papers by Elizabeth Gardner and Bernard Derrida, one in 88 and the other one in 89, both in Journal of Physics A, that address this problem, again, using very sophisticated techniques from statistical physics. And then that triggered enormous activity. You know, all the physicists that had a background in statistical physics got very excited. There was a lot of work in the 80s on putting Hopfield networks, everybody connected to everybody, put them on a lattice, put them with dilute connectivity, which is a bit closer to the brain, an enormous amount of papers. But what is more interesting, I think, is a recent upsurge. I mean, I recently read a paper that said, the title was "Hopfield is All You Need." And it's a very interesting paper. Dima Krotov is one of the authors. And there is a lot of activity in what is called dense associative memories, which is, again, this idea of storing memories as fixed points and using the dynamic of the network to find them. It's a fantastic idea. And even more recent, there is a connection to these dense Hopfield networks and transformers by choosing the appropriate nonlinearity function so that the derivative of the nonlinearity is equal to a softmax function, a Boltzmann distribution. Then the update rule for the Wij's, the way you learn the Wij's, becomes equivalent, or you can show mathematically that the equivalence, that it becomes equivalent to the attention mechanism using transformers. So now you can look at the transformers from the point of view of collective dynamics, energy, basis of attraction, and all these concepts that are commonly used in statistical physics. And it also opens the idea of studying new transformer architectures based on that idea of associative memories. So it's just to show you what a powerful idea this really was, not only in the 80s and the 90s where it triggered all this amount of work, but now is reformulated, because the powerful idea is not the Hopfield model, but is this idea of computing through collective dynamics and computing with attractors. These are the basic concepts that you have to keep in mind. So let's leave Hopfield for a while and go to the second Nobel Prize, that is Geoff Hinton. So Geoff Hinton proposed this Boltzmann machine, which is, so you can ask, what is the Boltzmann machine and how does it relate to physics? So you start with the probability distribution. So now really it's crucial to abandon this discrete binary idea. So you propose that the probability distribution of your inputs, X, which can be images, could be quantum states, could be conformational shapes of a protein. People use Boltzmann machines in a variety of settings, is of the form e to the minus beta, an energy that depends on X. So again, we have the idea of an energy landscape that is going to allow me to compute properties. So if you propose, this is a postulate, let me propose probability distributions of this form, which can be almost anything. It's just for me to find the energy that makes the probability distribution a good model for what I actually see in the world. So the probability distribution is of the form e to the minus beta e 1 over z. I can sample this probability distribution using Monte Carlo methods, or if I know the probability distribution, I can compute the average of any quantity f that depends on x. I can do the integrals over x of f of x, p of x, and that is going to be the average of x given within that model, the model that I have constructed, the way I have decided to model the probability distribution. So this again gives me the idea of energy-based models. So we have a probability distribution of this Boltzmann form. The energy E of x is going to be determined from parameters. And I'll tell you what is the basic idea in a moment. And now as we have the parameters for the E of x, then we have a model for the P of x. So how can we construct a model for the energy? And this is a very, very powerful idea that goes all the way back to James in the late 50s, last century again. And the idea is that you can only know what you know. So I is an index for all the things that you can measure. What can I measure about this system? First order correlations, second order correlations, higher order correlations, entropies, whatever, symmetries, scales, whatever I can measure about the system has to constrain the energy, constrain the probability distribution. And the idea of James was, that's all you know, and you should acknowledge that everything else you do not know. You only know what you measure. How do you reflect your ignorance about everything else? You reflect your ignorance by using a maximum entropy principle. So you construct the maximal entropy distribution that is compatible with being constrained to the things that you measure. Okay, and except for that, it should be as broad as possible. Remember that entropy is very small for a distribution like this and very large for a distribution like that, right? So everything that is not constrained should be as broad as possible. It cannot be constant from minus infinity to plus infinity because it's not integrable. But imagine a Gaussian with a very, very, very large variance, something that can be integrated, but is very unspecified, very broad. Then James showed in his beautiful idea that if those are the observables, that you know the averages empirically from the data, then your energy function should be a linear combination of those observables. And the coefficients of the linear combination, these Lagrange multipliers, lambda i's, are the only parameters of the model. These are the parameters that you have to figure out. This is your learning problem now. These are the parameters that you have to determine in order to completely specify your model. But again, we are in the world of energy-based models, right? And the beautiful idea of Hinton and Sosnowski in 83, and then Ackley, Hinton, and Sosnowski in 85, is to use two layers. To use your visible layer, these are the x's, whose p of x you want to model, and then you put a layer of hidden variables, h. So the probability distribution is a joint, it's a p of x and h. which is of the form e to the energy of x and h divided by c prime. These c's are just normalization constants. They are the integral of the numerator to make sure that the thing is a properly defined probability distribution and that it integrates to 1. Okay. And then if I know the p of x and h, I can marginalize. If I sum over the h's, I get the p of x, right? P of x is the marginal of the joint, whilst I take the trace over all the values that the h's can take. And the idea was a fantastic idea. The idea was that I am going to allow for local fields in all the x variables. I'm going to allow for local fields in all the h variables, but I'm only going to allow pairwise interactions between a hidden variable and a visible variable. There is no pairwise interactions between the x's. And then you say, but then how am I going to model correlations? How can this x be correlated to this x if there is no direct connection between them? Is mediated by the hidden variables. So these pairwise correlations are hidden in the model. The only bilinear interaction is between hidden variables and visible variables, the x's that you really want to model. So this was a very, very powerful idea. So this was the idea that you're going to model the probability distribution over x and h as an e to the energy divided by normalization constant. And this is the form of the energy. The x's, each one of them has a local field that I call here a sub I, multiplied by xi sum over I. The h's, h alpha is multiplied by its local field b alpha sum over alpha. And this is the only interaction term where an xi talks to an h alpha via a matrix wi alpha. So there are connections for every pair of hidden and visible variable, there is an interaction. And if which parameters do I need to learn then? I need to learn the a sub i's, the wi alphas, and the b sub alphas. And once I have that, I have my energy, I can sum over h to take the trace over h, and I can obtain my p of x. And this was a very, very powerful idea. Again, this is the energy, and these are the parameters, the a's, the w's and the b's are the parameters you have to determine. And the idea is you're going to do them, to obtain them through the data. So the model predicts a probability of the data. So you take the log likelihood of the data. Actually, you should take, the argument that maximizes the log likelihood, or the argument that minimizes minus the log likelihood, which is the energy. And over the parameters wi alpha, a sub I, and b sub alpha. And then you do gradient ascent or gradient descent on the W space or the A space or the B space. You find these parameters by doing gradients on this log likelihood function as a loss function. And it's very, very nice. It's a very, very elegant derivation that is just a difference between, for instance, for the wi alpha, is a difference between the xi h alpha correlation computed with the probability distribution, which is your current model, minus its value computed with the data. That's an error signal, right? The data should be getting closer and closer. The probability distribution in the model should be getting closer and closer to predicting the data or fitting the data properly. So this is equivalent of a learning error that you're trying to minimize, to bring to zero. So this is a great idea because it introduced the notion of this restrictive Boltzmann machine as generative models. They were actually, to my knowledge, the first example of a generative model. You know, now we have diffusion models and variational autoencoders and GANs, and we have all sorts of methods for doing this. But the idea was that from the data, you get this probability distribution. And once you have trained the machine, you use it for generating new data that are new examples, not in the training data. So the typical is you use the old database of handwritten digits to train your Boltzmann machine, and then the Boltzmann machine will generate new instances of those digits. And how does this connect to things that are closer to what we do today is through the notion of the deep belief networks, right? The deep belief networks were also a brilliant idea. not the idea that Hinton gets the Nobel Prize for. Hinton gets the Nobel Prize for the Boltzmann machines that I told you about. This comes a little bit later and is not cited in the prize citation. But the idea is the first layer here is a Boltzmann machine. It's a restricted Boltzmann machine with a visible layer, which I call V1, and a hidden layer, which I call H1, because this is the first restricted Boltzmann machine. And then you stack it with the second one, in which now this becomes visible and this becomes hidden. And then you stack it again with the third one, where this becomes visible and this becomes hidden. So you get this deep belief network where you, in an iterative sequential manner, you improve your model, you improve your generative model, you improve your model of the probability distribution that is generating the data. And then eventually, if you want to do unsupervised learning, you can do a classification on this refined version of the data set. You can think of this as very sophisticated unsupervised learning that is a pre-processing of your inputs on which you then apply an output classification or do whatever you were after with those inputs. How much more time do I have, Anna? I don't see my clock in the computer. I don't know if to tell you a little bit about Perceptrons. About 10 minutes. I'll tell you a couple of things about Perceptrons. You all know this, but just to close the, to tighten it up. So a perceptron is again the same McCulloch-Pitts neuron. You do what we call now a linear nonlinear model. You have an n-dimensional vector x, a scalar output y. You do a linear combination of the components of your vector x. You add this effective bias, which is the bias minus the threshold, and you apply to it a nonlinearity. If the nonlinearity is a step function, what separates positive y from negative y is the plane where y is equal to 0. The plane where y is equal to 0 is when this linear combination is equal to 0. This linear combination equal to 0 is the equation of a hyperplane in the n-dimensional space of the input. So the inputs are x1, x2, xn. This equation says, if you forget W0 for a moment, the equation says the x's have to be perpendicular to W. So you take the W vector, you take the plane perpendicular to it, that's the hyperplane. And the W0 is just a displacement of that hyperplane. So this is a picture. This is the plane where, okay. This is the plane already translated. The plane Wx equal to 0 goes through the origin, and you translate it for W0. On one side of this hyperplane, all the y's are positive. On the other side of the plane, all the y's are negative. So this allows you to classify. And it doesn't have to be a binary classification. Could be, if you use the appropriate nonlinearity, could be even a sigmoidal classifier or a logistic classifier, but it's still linear. Everybody in a plane will produce the same output. Every plane perpendicular to the W vector is equivalent in the sense of the response that you will receive. So if you need to vary the output, your only chance is to vary where this hyperplane is located along the direction indicated by the W vector. So we are stuck with linear classifiers. And then this is the kind of things that Rosenblatt, he worked at Bell Labs also, didn't he? Like Rosenblatt. Rosenblatt also worked at Bell Labs at that time, I think. No? I don't remember. But anyway, in '62, he wrote a paper that is called Principles of Neurodynamics. I love the titles of these old papers. Perceptrons, you cannot read. Perceptrons and the Theory of Brain Mechanisms. Imagine if I wrote a paper now that was titled The Theory of Brain Mechanisms, I would be whistled out of the room. Who knows what's the theory of brain mechanisms? But these guys were fearless. Perceptrons and the Theory of Brain Mechanisms. Anyway, so here he is with his mini computer, as you can see. These kind of computers require a lot of cooling and took big rooms. And he is implementing this perceptron as a classifier. And then we go back to the problem of linear separability. How many functions are there that I would want to implement, even if I'm just Boolean, from n binary inputs to one binary output, 2 to the 2 to the n? Then Cover, who was a very smart mathematician at Caltech did a calculation of how many separable functions, linearly separable functions are there from n inputs to one output. Everything binary again. We're back to in the Boolean world. Well, 2 to the n squared divided by n factorial. So 2 to the n squared is much smaller than 2 to the 2 to the n. And on top of that is divided by n factorial. So if you take the ratio between the number of separable functions and the total number of Boolean functions, in the n to infinity limit, that ratio goes to 0. So as n becomes bigger and bigger, the fraction of functions that are linearly separable becomes smaller and smaller and smaller. So Minsky and Papert, who were at MIT, got very angry about this. He said, okay, this guy Rosenblatt has an algorithm for training these single layer perceptrons. Perfect, we are very proud, he's very proud. But this can only implement linearly separable functions. Most functions that you want to implement are non-linearly separable, and we have no mechanism for training a machine that can implement them. So they said, off with their heads, forget about these neural networks and these perceptrons and these McCulloch-Pitts neurons. And they published, Minsky and Papert published a book actually in 1969 that essentially killed the field. I mean, everybody who worked on artificial intelligence was working on expert systems and asking, people, lawyers, how do you solve this problem? And doctors, how do you solve this problem? And trying to write the code that would implement that. That was the end of it. But then people thought about it more carefully and said, okay, so this is your perceptron. But if I have an extra layer that is wired appropriately, that pre-processes the input, then I can implement any function. And this was called universal approximation, universal approximator theorems. It was done by Sivenko and by Barron. So now we are, getting to be in the 80s. And this is what is called a NK1 perceptron. So you want to go from n inputs to k units and then to 1. We know how to train these guys. We can use the perceptron algorithm for training these guys, but how on earth are we going to train these guys? So every one of these nodes that has n inputs requires n plus 1 parameters. Remember the W0 and then W1, W2 to Wn. How are we going to get them? We have to learn them, but how are we going to learn them? Well, that solution took 15 years, believe it or not. It took 15 years to solve that problem. And the answer, of course, again, like Hopfield saw in his 84 paper, is to forget about binary, forget that the brain is going to operate with zeros and ones, forget that we need to compute when we build an algorithm with zeros and ones, and accept the fact that these variables are continuous. And once the variables are continuous, you can define a landscape in a continuous space, and you can take gradients to solve the problem. To try to find a minimum is the crudest way of solving an optimization problem. But if you insist on a binary language, you cannot take gradients and you're stuck. So the famous paper of learning representations by backpropagating errors, which is what makes the living of, I will guess, a significant fraction of people in this room, is from 86. It was a paper by Rumelhart, Hinton, and Williams. And again, it's not what Hinton is getting the Nobel Prize for, but because actually it was, as all beautiful ideas, it's a very simple idea, right? The basic idea is that you can do gradient descent by applying the chain rule. And I don't really need to tell you anything about backpropagation. You know that. I want to say a few words about neuroscience to finish, because in my own work, I continue to be inspired by Hoffield's ideas in the sense that the brain is also a dynamical system. It's like a recurrent network. It has sometimes layer structure, but even as it goes from layer to layer, there is an internal dynamics within each layer that makes each layer a recurrent network. And so the idea of computing through dynamics and the idea of computing with attractor is still prevalent. So I want to give you a very simple example. This is a monkey doing a task that humans can also make. It's called a center-out task. There is a target at the center, 8 targets around it. One of them leads up, and then the monkey waits for a go signal and has to make a reach to that target and come back. It just takes a few seconds. So it can make many reaches, and the regions, of course, are chosen randomly. So the monkey never knows which target he's going to have to implement next. The delay period between the appearance of the target and the go signal is just a couple of seconds. So while the monkey does that, we record neural activity by implanting an electrode in, as I said, the primary motor cortex, which is, think of it going from year to year. The right side represents the left part of your body and vice versa, right? It's contralateral representation, but there is a homunculus, there is a map of the body. So we can put the electrode, if the monkey is right-handed, we can put the electrode in the arm area that controls that arm and measure neural activity during these range movements. And we get data that look like this. These electrodes capture of the order of 100 neurons, these multi-electrode arrays. And this is about 20 seconds of data. Every mark is an action potential, it's a spike emitted for the neuron. Every row is a neuron. Every tick is a spike emitted by the neuron over 20 milliseconds of data. And of course, we want to play a decoding game. We want to say, okay, the yellow target was presented, the targets are color-coded. The yellow target was presented, then the red one was presented, the blue one was presented. If I don't show you the targets, but I just show you the neural activity, can you take a window of about 300 milliseconds around the go signal and tell me which was the target for that particular movement? Can you decode the neural signals? Can you do neural decoding? So you can start in a stupid manner to say, okay, let me visualize it. Let me pick 3 neurons at random, 78, 70, and 46, and plot this in a 3-dimensional space. So now I take a little, I'll take a little bin of 5 milliseconds or 10 milliseconds. I compute. No, actually, sorry. I take this 300 millisecond bin. I compute the firing rate during that bin. I put a point in this 3-dimensional space where I'm only looking at the activity of 3 neurons. And after all the points are there, I color them according to the target, which was the target in that particular reach. And as you can see, this is a mess. There is no structure, things don't cluster. It's very hard to believe that from looking at the position of a point in this space, you will be able to predict what the target was, because a point of one color is surrounded by points of all the other colors. So, but it turns out that this is not as hopeless as it looks. It's just a question of using a bad method for dimensionality reduction. The way to look for dimensionality reduction in this system is not to pick 3 neurons at random and plot them, is to use a real method for dimensionality reduction. So this is simply looking, this is just simply factors analysis, which is a slightly sophisticated form of principal component analysis. It defines specific directions in neural space, not neuron 40, neuron 46, but a principal component, another principal component, and another principal component. These are the 3 axes that I call neural modes, because every mode is a particular linear combination of neurons. It's a direction in neural space. And I have this neural mode 1, neural mode 2, neural mode 3. And now I put the points in that 3-dimensional space. And after I put the points, I color-coded, and it's like, it's fantastic. We were playing with this, and we were scooped, actually, by, oops, you don't see the reference. It's a paper by Santana. It's a paper from the lab of Krishna Shenoy, essentially, at Stanford, and the paper came out in the Journal of Neurophysiology in 2009. So when you color code, you see this amazing structure. First of all, points are clustered. All the points that were reaches to the same target are close to each other. Moreover, and this was an amazing surprise, look at the order, kind of purplish, red, orange, yellow, green. Purplish, red, oops. Something happened. Well, it's the end. Do I need my power supply? You think it's never happened for an hour? Sorry about that. Well, actually, I'm done. Essentially, what I want to show, so I can tell you words, what's the end of this. So the idea is that in this very sophisticated, think of the neural space as a space where every axis is one of the neurons. In this neural space, I have found a 3-dimensional hyperplane, essentially, which is spanned by these 3 neural modes. think of them as principal component 1, principal component 2, principal component 3. When I project all the data into this 3-dimensional hyperplane, which is living in a very high dimensional, I've recorded 100 neurons, it's living in a very high dimensional space, I see the structure of the data. And the structure of the data is not only clustered the way I wanted it to be clustered according to the target, but it's organized in the same way in which the targets are organized in the external space. This is such an, to me, it was amazing because it's such an abstract representation. Okay, so once we saw this result is now 14, 15 years old. Everybody who was working in motor cortex, like I was working with my collaborator Lee Miller at Northwestern, who works in a monkey lab, began to look at different tasks and ask whether other tasks also had this kind of low-dimensional representation. And we kept on finding these manifolds. Not all of them were flat. In this case, we were able to get away with factors analysis or principal components with a linear method for dimensionality reduction. In many cases, these manifolds were not really flat, were a little bit wiggly, not very nonlinear, not like a Swiss roll, just a little bit wiggly. But we still began to use autoencoders and isomap and different methods for nonlinear dimensionality reduction in order to find them. And we've kept on finding these manifolds, which are task specific. So essentially, when you learn a new motor task, you reshape the connectivity of the network to acquire a manifold representation. If you're a musician or a sports person and you keep on practicing, why do you keep on practicing? They say is to, what is it? They say is to preserve muscle memory, but that of course is just a way of speaking because our muscles don't have any memory, they're just elastic bands. The memory is in the brain. And what you're doing when you practice is you stabilize the manifold. You stabilize the manifold associated with this task. So how does this connect to Hopfield? In two ways. First of all, these manifolds are locally attractive. When somebody, my prefrontal cortex takes my brain, tells my brain that now I want to have some tea, it has to put me in the reach manifold, reach out with your arm manifold. But it doesn't have to put me exactly on the manifold. It just has to put me sufficiently close to the manifold. And then the dynamics will take me to the manifold because these manifolds are locally attractive. Not large basins of attraction, because if they are very large, they begin to interfere with each other. So there is a trade-off between having some basin of attraction so you don't have to be so precise in hitting the correct manifold, and at the same time having these manifolds for separate tasks sufficiently separated from each other. But we find all sorts of tasks, and they are very low dimensional in the laboratory tasks, but there you could say, well, you know, the monkey sitting in a chair reaching, this is very simple task. Of course, you have a 3-dimensional representation, but what if the monkey is doing, you know, monkey things, grabbing and eating and scratching its own back, and what do you find then? So we have now a whole new generation in the last 5 years of experiments in where the monkey lives in a fairly large cage in an enriched environment, so it's doing a variety of things. And of course, we don't find 3 dimensions, we find higher dimensions. We find 5, 8, 10, 12 in one case, but we never find 100 dimensions or even 50 dimensions. So all these task representations are low dimensional. They are not attractive fixed points, but they are attractive manifolds. And then it's the dynamics in the manifold that performs the computation. So if instead of showing you 1 point per reach, I now go back and follow the trajectory as a function of the reach, you will see a beautiful structure, but you have to believe me because I cannot show you. But you see petals, you see 8 petals that say, I went and came back, I went and came back. And each one of them has a color corresponding to the target, and they are again ordered in the same way in which the targets are ordered in the external space. So it's a beautiful way in which the brain uses Hopfield ideas, or in which a beautiful way in which Hopfield captured a basic principle of computation, which is to use population dynamics as a way to process information and to use these low dimensional representations as attractors, not necessarily point attractors, line attractors, manifold attractors. And then the question is, and that's the last question I want to leave you with, the question is, why would the brain organize itself like that? So to me, it was very revealing, a paper that appeared in iClear in a couple of years ago. And I'm sorry, I cannot read the reference, but I'll post it. It was an analysis of ImageNet. So ImageNet, if you remember, is not 256, but it's 200 something by 200 something by 3 every image. So it's a order of 150,000 pixels. So every image in ImageNet is a point in a 150,000 dimensional space. But not every point in that 150,000 dimensional space is an image, right? Most of them, if you just draw it at random, it will look like salt and pepper noise, well, color noise, because you have 3 levels of color. But what is interesting is there are, I think, 10 million images in ImageNet, 14 million, I forget, more than 10,000 categories. So you ask yourself, where do these images live? And these guys did a very interesting study of the dimensionality of this data set. And they use this nearest neighbor method, which depends on the parameter, which is how far away would you go to define your neighborhood. And as they vary this parameter, they got dimensions between 25 and 45, never larger than 45. 45 dimension manifold contains these 14 million images that live in 150,000 dimensional space. Our brain evolved receiving inputs, visual inputs, auditory inputs that are strongly correlated. They don't fill the whole space of all possible frequencies, of all possible illuminations of the pixels. The stimuli that we receive live in a low dimensional space. So our brain has developed a strategy to capture relevant inputs that live in low dimensional spaces, and therefore generate low dimensional representations of these spaces. And I'll finish by giving you another insight that we got from this manifold analysis. As I told you, in this very simple task, we got away with constructing a linear 3-dimensional manifold, but in most cases, we will need to use nonlinear methods because the manifolds are nonlinear. So now we are beginning to study systematically what people call the sensory motor pathway that starts with the sensory input until you decide on an action. And that requires, going through visual cortex, then parietal cortex, sometimes prefrontal cortex if decision-making is involved, and eventually premotor and motor cortices. So we follow the representation of the task as we go from cortex to cortex to cortex, or area of the brain to area of the brain to area of the brain. And what we find is that we start with a very non-linear representation in visual cortex, and we end with a very almost linear representation in motor cortex. So as you go from region to region to region to region to different brain areas, the brain linearizes. And why would the brain do that? Well, visual images are very nonlinear. If you have a caricature made of you, it's just edges, and people can recognize you. So the edges, which are very nonlinear objects, it's not the way in which the luminance changes smoothly across your cheeks. It's the edges that define the object, right? So that's a very nonlinear set of features. So it's not surprising that the visual representations are very nonlinear. But why would the brain linearize as you go through this sensory motor pathway? It linearizes because the motor cortex, which is the output of the brain, has to control a plant. And the plant is your body. Has to control all the muscles that change all the joint angles so that you can move in the world, you can talk, you can grab things, you can do everything that you do. It's much easier to implement linear control than nonlinear control. Much easier to adapt, much easier to change. So it's a very powerful strategy to use at the sensory end nonlinear representations because the world that you're representing is nonlinear, and to gradually linearize that representation so that you control the plant using methods of linear control. So all these ideas of attractors and manifolds, which is what I work on now, and really go all the way back to John Hopfield. Thank you.
So thank you so much for a great talk. I wanted to start with a very general question. So we talk a lot about how physics, how neuroscience, how machine learning interact with each other, how they influence each other. I wanted to ask a question. So what are the future challenges, the questions that you think are important to answer in order to help machine learning further develop, in order to foster the interaction between neuroscience and physics and machine learning?
So the interaction occurs at many different levels. So a lot of people who manage large data sets in physics, the astrophysicists, and some of the people who do quantum systems, use machine learning methods as tools. It's like, 30 years ago, you use your R package for statistical analysis. Now they use machine learning methods for statistical analysis. But I don't know if I would call that a scientific interaction. I would call that a new toolbox became available, and it's very good to know about it, and it's very good to use it. And you have to learn a little bit in order to use it. But I wouldn't say that they certainly do not contribute to the evolution of machine learning, because they are just users, right? It really is like pressing a button in any statistical package. Then there is theorists, like people like Surya Ganguly at Stanford, who come from a background of statistical physics, who tried, for instance, when we started training multi-layer perceptrons for pattern recognition, we said, why don't we get trapped in local minima? In principle, you go gradient descent, depending on your initial condition. The landscape is like this, and there is a good minimum here, and there is a lot of minima that are not good at all. You start here, you go down, you get trapped there, you're very far away from the global minimum. But we didn't have this problem. We knew empirically that this was not a big problem. Why not? And then, like 5 or 6 years ago, Surya had this beautiful paper where he studied the learning problem, and he found that in these very high dimensional spaces, most of the points where the gradient vanishes are actually not minima, but saddle points. So you went down, you feel trapped, you try, you kick it yourself a little bit, you're trapped, and eventually you find the direction that allows you to keep on going down. So it's not an energy barrier, it's an entropy barrier. It's a question of you introduce a little bit of noise to untrap yourself, to get unstuck from that point, and the noise has to be in the right direction. But if it eventually finds a way to go downhill and allows you to keep on going downhill. So now I know why we didn't get trapped in local minimum. So that, I think, that's a fruitful interaction, because it allows you to understand conceptually why people from machine learning can propose a method and is amazingly successful beyond what you would have expected. But why does it work so well? So this is where people with a more theoretical background, and not only statistical physics, people who do theoretical computer science. So many years ago, people who do pack learning, probably almost correct learning, also contributed a lot to our understanding of how learning would proceed when you couldn't fully learn the task, or when the examples were very noisy. There was a lot of understanding of what was the meaning of best approximation in that. Now, typically computer science uses tools based on worst case analysis, while statistical physics uses tools based on average cases. So they are complementary approaches. And I think those approaches are a scientific collaboration, because then one can help make progress in the discipline of machine learning by understanding better the underlying mechanisms, and eventually, maybe even if you're lucky, propose an improvement that comes from that side and not from the more empirical side. But the very prevalent use, people who do quote unquote data science, which they are users of tools. And I see that as very important, but it's an engineering purpose and not a science collaboration. It's a different, it doesn't involve this conceptual search on the tool itself. It's a conceptual search on the problem they are trying to solve. I don't know if that answers your questions.
Please feel free to ask any questions, guys.
For the principal component analysis for the monkey. You get like 5 principal components that you need. Could that just correspond to the number of degrees of freedom, the joint angles that are required to do the grasping?
That's a very interesting question. No, because the number of the muscles are also correlated. So the number of effective degrees of freedom that you need to operate the arm in a given way is not just simply counting the number of joint angles that you need to control. There is also a manifold in joint angle space. And the task corresponds to a manifold. So the number of effective degrees of freedom that you need is the number of the dimensionality of that manifold, essentially. It's smaller. The number of joints will give you an upper bound for sure. It wouldn't be low. And that also explains the low dimensionality, because we have hundreds of muscles in the body, but we have billions of neurons in the brain, even in motor cortex. So clearly, we are over-dimensioning neurons compared to the number of degrees of freedom. Even if we had to control each one of them individually, which we don't, it will be much smaller than the number of neurons.
Hi, Professor. Can you hear me? Okay. Thank you again for your talk. So one question is more regarding to the final thing you said, actually, where you basically would justify the feature learning process basically of the brain as a way to basically overcome mechanical limitations of organism. Basically, we want more linear features basically in the end, because linear control is easier than nonlinear control. But like we know in deep learning that usually good features are also features which can be used by linear classifiers, linear models.
Right.
So would you say that, and those features are usually better for generalization? So would you say that the ability of humans to generalize is a consequence of those mechanical limitations, and why other organisms may not be able to be intelligent because they don't have those like?
So, you know, when I think of deep learning, I think of the top layer. And the top layer is a perceptron. And the top layer can only implement linearly separable functions. So the way I think about it, and it might irritate some of the serious deep learning people, all the rest is a preprocessor, so that at the end you can do the task, you made the task linearly separable, because the last layer can only do the output can only be a linearly separable function of the activity in the preceding layer. So all the previous work has been to make it happen. And in that sense, it's a little bit similar to what I'm telling you that the brain does, right? By linearizing eventually through the sensory motor loop. Whether this is true for other organisms is a very good question. I am going to a workshop at the Simons Foundation on Thursday and Friday about cephalopods, which are like, you know, and now I can only think of the Italian words, calamari and pulpo. And so what are the words in English? Squid and octopus, thank you. For some reason, you can see that I've been eating seafood recently in Italian restaurants. I couldn't think of the English word. So these guys, the tentacles don't have joints. It's like a rubber band. So how do you control that? How do you control something where every centimeter is a different degree of freedom? Moreover, how do you control that locally? Because they do a lot of control without invoking the central system. And it reminded me of a very eccentric colleague that I used to have at Los Alamos that had designed this and fabricated these quasi-insects that would have 6 or 8 legs and that would crawl on his windows. And they have no central controller. The control was just a feedback on each leg. And how did this, I mean, you can imagine one leg would go this way, the other way would go that way. How is it coordinated without a central system? What is the mechanism that creates the necessary correlations? But he was a very inventive guy, and he had attached little cleaning paths to the legs. So his windows were always very clean, because these fabricated insects were, moving around the windows all the time, and eventually the windows got very clean. But these are very provocative questions. To which extent do we need a central controller? And it's a very important question in robotics also. How much can be done with the local control, and to which extent do you need the coordination and the covariance of the correlation that you can only obtain by communication? So you cannot control every limb independently. So I don't know if I answered your question, but can you please explain the physics associated with the attention? No, I cannot explain it in Francesco. I cannot explain it in short words, but I'll send you a reference. Yes, this lower, when the recent nonlinear dimensionality reduction approaches that we've been using, I don't know if it's recent, but we use autoencoders, of course, and we use, we mostly use autoencoders for nonlinear dimensionality reduction. We use isomap also. Isomap has the advantage that there is a limit in which it becomes principal component analysis, so you can anchor your results. I always like to have some limit in which I know exactly what I'm doing when I have an algorithm that depends on parameters and arbitrary choices. This question of the lower dimensionality map across animals is very interesting. So this manifold that I showed you for this very simple rich experiment, we can map for a given animal across time, up to a couple of years. We can map across monkeys. We can align the representation of monkey A to the representation of monkey B. And a few months ago, we have now data of a man who has a spinal cord injury, who cannot move his arm, but he thinks of moving his arm by looking in the same sequence of targets. So he's looking at the monkey executing the task, and he thinks of going to the red target, going to the blue target. We measure his neural activity. We align it to the neural activity of the monkey doing that task, the same low-dimensional representation. We use the decoder on the monkey to understand how the muscles are going to be affected. And we use this predicted muscle activity to activate transcutaneously the muscles in the arm of this man who cannot move his arm. And the arm moves and reaches to that target. So among mammals, what I'm saying is that a human primate and a non-human primate are not very different in a representation. So monkey A to monkey B works, and human to monkey also works for this very simple task. Of course, a human could be playing a piano sonata that a monkey cannot play. So, and what is the manifold? The dimensionality of the manifold associated with the piano sonata is probably higher than 3. I mean, because the complexity of the task determines how many degrees of freedom do you need to have available in your manifold. But certainly, there is a lot of correspondence, at least in a lot of elementary tasks that, for instance, in the case of the translational to medical applications is very important, because for a person just simply to be able to reach and bring something to his mouth is an achievement if you're a paraplegic, and it's not that it's not very sophisticated, and presumably doesn't require a very high dimensional representation. I think I answered those 2 questions.
Can you say something about the like transformers used in cross-modality architectures as it relates to like human and brains cross-modality ability, like synthesizing image and text data, or like encoder-decoder architectures, and how we might make use of neuroscience to improve either like sparsity or compression in like information sense?
Actually, when I began to read about transformers, I was hoping that transformers would help me understand attention in the brain because the attention mechanisms in the brain are very poorly understood. So eventually, maybe as we understand the attention mechanisms better and we understand transformers better, there might be some kind of cross fertilization there. But so far, there isn't much that I can tell you about how the actual brains implement attention to be able to make suggestions about how to make transformers better. Thank you. So you should have. Oh, thank you. Oh, what an honor. Thank you very much.
Stand for a photo with me and Larry.
Of course.
Very nice. Beautiful talk. Thank you very much.